So let's start our session before lunch. And now we'll have a Lihwai Li.
Okay, so my name is Lihwai Li from ASIAA. So thank you, Science SOC for giving me this opportunity to present my work. So this study is done based on two observations. One comes from this slope manga survey, which is an IFU observation for 10,000 galaxies. And this is the project that my colleague Yan Ting and I joined as an associate member. At the time, Paul was a director here, so we are very grateful that Paul strongly supported us to join this project. So the second component observation comes from ALMA, which I will describe a little bit later. So my focus today is concerning this galaxies located in the Green Valley region. So these are the galaxies are thought to be in the transition from star-forming phase to the Barson phase. So they are ideal targets to form the quantum mechanism in galaxies. So we know that there are very different ways that can suppress or shut off the star formation inside galaxies. So some of these processes are involving the removal of the cold gas or even the hot gas, such that the gas will not have subsequent star formation. So in that case, the molecular gas fraction, which is defined as the cold gas mass divided by the stellar mass, will be reduced. On the other hand, there are some other processes that are not necessarily removing the gas, but they could introduce some turbulent motion into the gas, such that the gas cannot form stars efficiently. And in this case, when we measure this so-called star formation efficiency, which is the star formation rate divided by the H2 mass, you will have a lower value. So by having these two measurements, one can get some insights about what's going on inside galaxies. So to have those two measurements, basically you need three parameters: the star formation rate, the stellar mass. These can be obtained using the optical spectra of MUSE. However, MUSE does not offer the gas mass measurement. So this is why we need to add another millimeter or submillimeter observations into our data set. So at that time, and I believe it is still true now, that the ALMA is the only facility that can efficiently offer the desired spectral and spatial resolution and also sensitivity over a larger sample. So this is why my collaborator Sarah Allison and I initiated this so-called ALMA Quest survey, standing for the ALMA manga quenching and star formation. So this is a combination of both manga and ALMA to observe 46 manga selected sample with 0, 1 to 0. So this sample consists of several classes of galaxies spanning a wide range in terms of their specific star formation rate, from starburst main sequence to the Green Valley galaxies. And one important feature about manga data is that with multiple emission line measurement, we can identify the primary ionizing sources for each subcomponent inside the galaxies. So we can classify the regions into like H2, composite, linear, or Seifert. So here we are mostly interested in two types of regions. One is the star-forming spectrals, and the other is the so-called retired spectrals, in which case we believe there is very little star formation going on. So with the combination of ALMA and manga, now we can measure these two properties that I mentioned earlier. So here is the star formation efficiency for main sequence galaxies in the upper panel, and this is for Green Valley galaxies. And we can also compare their H2 mass fraction between the two samples. So in the paper we published last year, we found that statistically, the green body galaxies have not only lower gas fraction, but also lower star formation efficiency defined using the CO. So the naive question we have in mind is that what is the origin that's driving the low star formation efficiency in these green body galaxies? So to answer that, we have to first keep in mind that the critical density of CO is like 10 to the third power per cubic centimeter. So CO basically not only traces the denser part of the molecular gas, but it also can cover the reduced emissions. So if we write the molecular gas SFE as a product of the dense gas fraction times the dense gas star formation efficiency, then you can see that the low SFE can be attributed to, for example, the lower dense gas fraction, or it could be due to the lower dense gas SFE, or a combination of both, of course. So to answer which one is more important, we further follow up some of our targets with the dense gas tracer, the HCl 120, HCl plus 120 for some of our sample. So here I'm showing the SFE and the gas fraction using CO for the entire Alma class galaxies. And the 5 yellow stars represent our targets for these dense gas observations. So you can see that we specifically choose those green body galaxies which has the comparable CO gas fraction as the main sequence galaxies, but their star formation efficiency actually differ by almost a factor of 10. So our purpose is to see whether these green body galaxies have a dense gas or not. So here I'm showing you the gas distribution of our 5 targets. So you can see that in all the cases, regardless whether they are main sequence or green body galaxies, they are all well detected in CO, HCl, and HCl plus. So this tell us that these green body galaxies might still have some amount of the dense gas. So the question is whether they are systematically lower compared to the main sequence galaxy or not. So with this data, we can first look at their Schmidt-Penka relation. So here is a plot showing the surface density of star formation rate as a function of the surface density of gas mass in CO, in HCl, and the HCl plus. And all the blue dots are for the subregions within the main sequence galaxies. And the green symbols are those inside the green body galaxies. So immediately you can see that the green body galaxy does not follow the trend formed by the main sequence galaxies. And this means that they have low star formation efficiency, either in the bulk molecular gas or in the dense space of the gas. So now we can come back to test these 2 scenarios. So the first one is whether the CO-based SFE depends on the dense gas fraction or not. So this is the SFE in CO, and this is the dense gas in different tracers. Again, the blues are for main sequence and the green are for green body galaxies. So first thing you can notice is that the distribution of this dense gas fraction between the main sequence and the green body galaxy are actually very similar to each other. So as a result, when you look at this plot, you don't actually see there is a correlation between these 2 quantities. So the SFE of CO is not sensitive to the dense gas fraction at all. And for the second scenario, which tests the CO-SFE versus the SFE in dense gas, now you can see that there is a very strong correlation. And the green valley galaxies have lower SFE in not only CO but also the dense gas tracer. And it's actually extension of the main sequence galaxies. So based on these two plots, we concluded that the reason that the green valley galaxy have low CO-based SFE is not because of the lack of the dense gas, but rather their star formation efficiency inside this dense gas is also low. So finally, we can put the green valley galaxies on this global Schmidt-Chemical relation together with other type of galaxies in the literature in order to discuss them in the border context. So now this is the star formation rate versus the gas luminosity. But this time, this is the integrated property. So that's the total star formation rate versus the total luminosity. So here we have post-starburst galaxies, the early top galaxies, star-forming starburst galaxies, and some subregions within star-forming galaxies as well. And the square blue ones are for the next sequence galaxy in our sample. The green ones is for our green valley galaxies. So you can see that majority of the sample, including the post-starburst galaxy and even the early top galaxy, they all fall into this one-to-one relation as the star-forming galaxies. So meaning that they actually share very similar star formation efficiency, despite that the gas content might be lower. However, only the green valley galaxies and also a certain fraction of the post-starburst galaxies, these are the transitional galaxies, they actually deviate from this main chemical relation. So they have relatively lower star formation efficiency. Right, so our conclusion from this study is that maybe the green valley galaxies really represent a very special and rare cases where you might have lower gas content, but the efficiency of those dense gas is very low. So something stops them from forming star efficiently. And unlike other categories, they all have nearly constant star formation efficiency. So this is my summary. So I presented this on our present survey, which can simultaneously provide the measurement of star formation rate, stellar mass, and gas mass at kiloparsec scales. And based on the CO observation, we concluded that the green valley galaxies have lower gas fraction and also lower SFE using CO as a tracer. And we follow up with those galaxies with comparable gas fraction as main sequence galaxies, and we found that the reason that these green valley galaxies have low star formation efficiency is not due to the lack of dense gas. They do have the dense gas, but somehow some mechanism prevent them from forming star efficiently. So I think that's all, and I'll stop here. Thank you.
Thank you.
So your last point is extremely interesting. I wonder if you can speculate what's preventing the dense gas. So since you have resolved spark source, have you looked at whether the gas is more turbulent, for example? That may be one reason it's lowering, enhancing tumor Q.
That's a great question. So with the data we have now, we cannot measure the dense gas velocity dispersion precisely because the acceleration is very low. But we do have the velocity dispersion from CO, which indicates that the green valley galaxies actually have higher velocity dispersion. So suggesting that they are more turbulent. So that could be the reason that suppressed the dense gas star formation efficiency. But even so, we cannot directly tell which physical mechanism that drives this turbulence inside the cloud. We don't see evidence of strong AGN, for example. We do have some lighter regions, but they could be just associated with the old stars, not necessarily due to the AGN. So I think a lot more work needs to be done. For example, we can get more transition long line in order to constrain the temperature and the density of the gas. But I think your speculation is right. At this moment, they are more turbulent in the field.
Thank you, Lihwai, for the talk.
Hi everyone, I want to thank the organizers for giving me the chance to present my work. This work is based in archive data using data JWST MUSE. My name is Carlos Lopez, and my collaborators are Lihwai and Sebastian Sanchez from Mexico City now. So in this work, we report the discovery of large structures in one of the nearby galaxies in the local universe. And here, stellar bursts are really important to study since a lot of galaxies in the nearby universe, in the high-energy universe, show the presence of stellar bursts. Approximately 2/3 of galaxies show these non-axisymmetry structures in the optical, and this amount varies depending on the wavelength we are observing. The detection of the stellar bursts depends as well on the spatial resolution of the data and also on the redshift that we are observing. For instance, here showing four different images of galaxies observed with different indicative photography galaxy surface, such as SAMI, MANGA, ASIAA, and more recent use paths. So here you observe that the stellar burst of every case is more or less well defined. But the detection obviously increases in the local universe. We'll be able to detect clearly various structures, right? So we might think that in the local universe it might be easy to detect stellar bursts because of the high angular resolution. So this is a classical example of a stellar burst. So we have the bar that is aligned towards a constant, more or less constant distribution, and we have characterized those names in a Lucas atomic ring. This is the typical galaxy that we think when we talk about stellar bursts, right? However, in our case, NGC 1087 is a very interesting case where we detect the presence of most likely a stellar burst or a novel distortion. Here, this is the MUSE-GRA image from this galaxy. So in the center, in the local region, it is not clear that this galaxy presents above the central region. The central region has very dusty lanes, right? This has a very diffuse irregular nucleus. In fact, there is not a well-defined nucleus. We have different bright spots, and probably the reason of that is because we have several of those lanes and probably an intense star formation. So at the distance of this galaxy, the full weak maximum resolution of the MUSE data is of the order of 6 parsecs. So we are observing galaxies at very high spatial resolution. This data is from the famous MUSE team. So if you observe the ionized gas in this galaxy, we observe some alignment of the ionized gas that we didn't observe in the self-absorption image. So if you make a zoom as well around this region, we observe this more or less elongated structure in the ionized gas. And if we plot the ionized gas, so the ionized gas is paired with the HR oxygen 3 and nitrogen 2 emission lines. So if you trace the DPT diagram or diagrams that are sensitive to the hardness of the emission, we will notice that most of the ionized gas trace here paired with the oxygen 3 over H beta and oxygen 1 or H alpha, which is a good light ratio sensitive to the H ionization. We will observe that most of the ionized gas in this region is totally compatible with star formation according to the polarization curve from QLED Tau 2006. And these are just some short models that, which we are not able to reduce the line ratios. So if we observe the zero molecular gas phase with the 2-to-1 transition, we will observe that in the central region there is a high concentration of molecular gas in concordance with the star formation that we observed in the H alpha maps. Right? Here I show you the public canvas resolution for this data in particular, which is available 110 parsecs. So we will observe a high concentration of molecular gas. We will observe star formation in the central region of this object. However, from the optical continuum images, it's not clear at all that we have the purpose of a bar. If you observe a much higher spatial resolution, in particular using the JWST in the atom microns, and here is the so this is the spatial resolution of the data is of the order of 3 parsecs at the distance of this object. We observe many different individual globular clusters. We will observe that the 2 microns emission, the unipolar emission, the line is totally aligned towards a predefined or a preferred position angle. So if we perform some isoplots, we will observe that the orientation of this structure is around 305 degrees, which is totally different to the position angle of the disk, the galaxy. Right. So just thanks to the high spatial resolution of the JWST, and thanks that we are observing the infrared balance in which, in general, observers are thought that they are all stellar structures. Most of the emission that we are observing here is most probably due to all stars, right? So if you want to observe stellar balance, it is better to observe in infrared balance. So if we perform a photographic modeling of the 2 microns emission, and this is another, this is the F300 filter from the JWST as well, which observes around 2 microns as well. We will observe that we have the same elongation structure and radius structure around the same position angle. So here's a model of the light distribution in both cases, and this is irreversible. So most of the infrared emission is concentrated in a very tiny region of the order of 400 parsecs, and the total extension of this structure is around 1 kiloparsec on the disk plane. And from here, we are more clear that most of the light is associated with a stellar bar. However, kinematics is also a tracer of the potential. If you observe the CO moment one, so the CO velocity field, H alpha velocity field, and stellar velocity field obtained from the ILS analysis, we observe in the central region there's a strong distortion in the simultaneously in the 3 different velocity maps. In fact, if we overlap the isovelocities over the 2 micron images, we observe that in the bar region, the isovelocity contours are twisted. Right? In fact, this is these are the price of an oval distortion in produced mostly by a bar. So this has been observed since the 80s, and this is an example of the observation from Penzical in the 84. So if we perform a kinematic modeling to subtract the circular rotation, and through this equation we will observe that the circular residuals which is basically modeling this equation and subtracting to the observed velocity map. We will observe that in the central region there are high velocity residuals of the order of 10 kilometers per second simultaneously in three different velocity maps. So this velocity translates to around 50 kilometers per second on the disk plane of this galaxy. Here are the rotational codes of the three different velocity maps. So in order to understand why it's producing such a large non-circular motion, we perform different non-circular rotation models that intend to describe the behavior of the kinematics of bars in galaxies. So one of the most popular is the bisymmetry model that takes into account the radiant and gravitational components of the particles in and above potential. So here are the quasi-elliptical orbits that follows particles, or at least that is what predicts the hydrodynamical models. So in the presence of, if we didn't have this lane, the particles in a bar would follow quasi-elliptical orbits. And this is the model that we try to model here. So if we apply this model to the observed velocity maps, we will see that we are successfully recovering the line of sight velocities simultaneously in the three different models. Here, in this model, we just have a parameter that depends on the position angle of the bar. So basically, we just fix the position angle of the bar to the one observed in the infrared. So we reproduce simultaneously the distortion with a bisymmetry model. However, in bar galaxies, we have some inflow process, right? We might have gas flowing towards the main axis of the bar, and this inflow will also be causing the observed non-circular motions in this galaxy. So we perform adopt non-axisymmetric inflow models, which follow this expression, right? And after doing this analysis inside the bar region, we find that an inflow model along the bar axis would also reproduce the observed velocity field. So both cases are possible scenarios or possible scenarios to explain the observed velocity field. So having computed the inflow velocity of the gas, which is of the order of 50 kilometers per second, we can estimate the associated molecular mass inflow rate. So by using this formula, this is the inflow velocity, this is the molecular mass orbital density, and this is the velocity distance. So it is quite straightforward to make this analysis. And we found that the average inflow rate is of the order of 20 solar masses per year, and the submeasure rate inside the bar structure is of the order of 0.1 solar mass per year. So we conclude that an inflow model will also explain the observed submeasure rate in this object. And this is also likely because in general, bars are thought that there are mechanism to inflow gas in the center of the galaxies. So the inflow model is also likely a good explanation. Here I just give my remarks and conclusion. So I want to say that bars are important to study, and it's important to understand the behavior of bars. And if we want to better understand this kind of behavior, we need to look also the kinematics, not only the photometrics. Thank you.
Thank you. Now, questions. So compared to the other bar galaxies, and this one, if you put this galaxy into the plot that we were just shown, the green valley diagram and sequence stuff, then what is galaxy? The location will be?
It's a Stockholm galaxy. Yeah, it will be located along the main sequence of this galaxy.
Thank you very much.
Yeah, it is still interesting because probably the submeasure that we are observing in the central region is most probably driven by the inflow motions along the bar. So bar will also explain the stop motion that we observe for instance, in bar galaxies. So maybe that is associated with the location in the stop motion.
Yeah, it will be a long trick for me to see in simulation how much the contribution from the interaction between the bar can contribute to the turbulent gas into its region, and to see how the turbulent motion increases, and to see whether it's important to lead a increase in the starvation.
Yeah.
Thank you very much.
All right, so the next talk on the schedule from Lawrence is canceled. So we're moving on to the next session in the program on magnetic fields and star formation. And so the next speaker is Hua-bai Li. And I'll turn it over to you, Hua-bai.
Morning, everyone. So this day come much earlier than I expected. I mean, who can connect the hole's energy to refinement? And this also forced me to announce something really premature, which is a survey dedicated to Paul using his telescope. And since I do not know much about ammonia, I can only do this. Right? It's a survey about correlation ball. Something I can do has not been done. And the motivation is like what Doc told yesterday, this formation is still a mystery. How this can form under this condition very strong in the field. And one theory is that maybe some kind of alignment of the angular momentum of B field can help. And if this is true, then we should expect the observed angular momentum and some kind of preference to align with the B field, like some maybe particular current. But this hasn't been possible to observe. But we see some light from our simulation. We see that the B field structures due to different alignment is so different that they can result in different patterns of correlation ball. So this is the motivation. Just one slide to show you that I'm not lying. Right? This indeed is working on this and it's submitted. And one of you is reviewing it now. And even more premature is the instrument we plan to use to the survey, which is GLT colorimeter. And we don't go into detail for these, but my point is that we will have a completely new methodology for this colorimeter, which I won't get into detail, but my point here is this won't be possible without GLT. Because GLT is not only a state-of-the-art instrument for state-of-the-art science, it's also served as a platform for either number generation, and what that means, right, to explore a new type of instrumentation. So to me, it's great lab for terrorism. So back to something I've already done, probably for too long already, is the interaction between gravity, turbulence, and magnetic field. We put this in together, it looks something like this. And the best tool or theory we have for these kind of structures is magnetic hydrodynamic equations, and here are some of them. And the most important one called the second one, which pretty much is F equal to MA. But here the F including the advection force, which is region of turbulence, thermal pressure, Lorentz force, gravitational force, and internal friction. And this kind of theory inspired observation. Lots of observation are actually trying to find out the relative importance between these forces. If you compare the turbulence term to the thermal pressure term, you got so-called Martin. Okay? And compare the turbulence term to the Lorentz force term, you got so-called the Evans Martin. And some of these observations, we have common sense of it, like these red values, the Mach number, Reynolds number, magnetic Reynolds number of the scale of the cloud. By the way, this is the ratio of the advection term to diffusion term in the reduction equation. But these people probably won't argue too much about this value. But for some values, especially related to magnetic field, people fight a lot about it, like the Evan Mach number, or most importantly, which is the main topic of today, is the magnetic criticality, which if you compare this gravitational force term to Lorentz force term, you can reduce this to this ratio, this mass to magnetic flux ratio. Of course, for the gravity to overcome B field to collapse, you have to go over some critical value of this ratio. And if we put these already well-known values back to the equations, since the ratio is so big, we can, for most of the occasion of the full molecular cloud, you can ignore the diffusion term, and you got to solve the flux freezing condition. And so the analytical studies almost 4 years ago, and also do numerical experiment on it. But in a nutshell, you can understand all these things by this cartoon. If it's just critical or subcritical, gravitational contraction can only have along the B field, you have this kind of a morphology. And B field is a constant of density. The other thing is that if you get very large criticality, the contraction can be isotropic, and you got the B field vary with density to the 2/3 power. But how large is large? We do a numerical experiment here to show that if you want to keep this 2/3 index, you have to be 10 times larger than the criticality. Okay? So a little bit larger, you won't get 2/3. Soon you will go back to flat, 10 times larger. And this comes a problem. Okay? If you look at observation, the two tracer of the B field, dust thermal polarizations, then you see this kind of reminds you of this kind of morphology. Okay? So it cannot be too critical. But on the other hand, you look at the Zeeman measurement, it gives you 2/3 index of the B relation, okay, which seems contrary to each other. And this is a data-long mystery here, and also summarized in the recent 57 review. But in fact, the problem is larger than this. We pointed out already 10 years ago that if you ignore about colorimetry data, you simply plot the same Zeeman measurement, not versus volume density, but column density, you got this kind of a plot. The good thing of plot with column density is that the mass flux ratio has the same dimension as the column density to B to strength ratio. So you can easily plot the criticality relations as this dashed line and dotted line here, or why there's a different line, different assumption of the structure. Okay. But what you notice is that you see the data, they can increase along the subcritical line, but when they hit this criticality wall, they cannot penetrate much. Maybe 2, 3 criticality above, but if the order of length is higher, it will be like somewhere like here, right? Even with the help of the arrow bar, you don't see much data can reach that point. So this is another, even more direct mystery about this situation here. And here I just plot Tao-Chung's fast data from last year, which was a fall quite well into this picture. So the summary of the problem is the Zeeman, B, and the volume density relation is hard to understand. Okay. So when this question has what happened here, and my best guess here is we'll probably compare orange and apple here. This is why we stuck with this mystery. Okay. So why the left-hand side in theory, the B A relation here are actually a time relation. Right? For each N here, each B here, is a snapshot of a collapsing core or cloud. Okay? And this can take millions of years. So you are not going to observe them. On the right-hand side, the observed relation is a snapshot of the current Milky Way. So I call it a spatial relation. So if you want to use the temporal relation to interpret the spatial relation, you better think twice. The way we think twice is using numerical simulation, but not just any numerical simulation. We calibrate our initial condition carefully with some information already, as what I showed earlier. We believe that the morphology was suggested some transbanding condition, and the B condensed relation suggests that you cannot be too good. So if we do this, then this is a result. We can trace core, there's 3 core here, and the column is different snapshot. So if you can trace 1 core at different time, you can have a temporal relation. And you take snapshot of the entire volume of the simulation, you got a spatial relation. So as shown here, the black line, the temporal relation, and blue and red dot, there are 2 spatial relations from different snapshots, about 1 million apart. So you see they're quite similar. You might notice some good news already. First is that the results of the core and the cloud look quite similar to the observation with ordered beam field. Shouldn't be surprised at this. We put this in. Okay. And what's really interesting is that the same simulation also replicates the 2 to the power of the spatial relation. And this is really interesting already. Okay. So it's kind of problem solved. One simulation replicates both observations. Okay? And all the core for me here are actually transcritical as expected. And also, for transcritical, you should have the temporal relation much shallower than 2/3. And as we see here, it's also agreed. So the only thing I think left to explain is then what is the mechanism behind this special 2/3 pattern. Okay? And this, I hope I can done in 1 minute, is using this plot. The answer is right here. So here I show is the turbulence velocity from different positions in our simulation. Okay? So you can see that, and here I put the critical line here. You have to go above the critical line to be superabelic. Okay? So you see for low density region, the red region here, they're all very subablanic. Which is not a surprise, this is what we put here. But what's really interesting is that as high density regions form, you see the turbulence energy got boosted, mainly due to gradual turbulence. And boosted so much that they can go above the Atlantic line. Okay. So all this dense region is slightly superabelic, and when turbulence becomes superabelic, it can compress the BLI in random direction. And in random direction, compression, statistically speaking, is the same as isotropic compression. So it will also give us 2/3. If I may, for another minute. If you think really carefully, then shouldn't this also deviate with B field morphology? Indeed, in our simulation, we go to small scale, but higher density, you will see deviation, which is here from the initial condition, increase. Okay, this one simulation, and this is not Chizo, this is my student, and Chizo's data is here. Chizo data is here. So in observation, we see the same thing if you compare single digit data and its spectrometry data from the same cloud. You see the same trend. You go to higher density, large deviation. Okay, I will end here with a quick summary. Is we can have one simulation produce all these observations. And the critical point, I believe, is we very carefully calibrate our initial condition, really with observation, not just the random phase, to put this value here. And the critical point we observed is that the Evermark number is actually a function of density. And this is why we can have ordered magnetic field and flat part from low density. And the way you go to high density, you got superabelic turbulence, so it will give you this slope here, and also more deviated B field at high density. Okay, thank you.
Yeah, time for one question.
That was great, thanks. The question that immediately comes up though is, if it is so simple, and I mean this with all respect, do we need the simulations? In other words, what's happening that's moving things from one component to another? Why can't I just write down the equations like Frank would do and say, aha, we were just missing this aspect. If we started with these initial conditions, we knew we had to get it. Is there something in the simulations that are important? Is there a mixing going on of the different, let's say, energies or something that I need to run the simulations to give me?
Okay. I think the most right answer is turbulence. Turbulence is so difficult to predict and to put into the equation. It's in the equation, as in this reaction term here, but as it evolves, how to predict. Also, the gravel turbulence, how much the gravel turbulence can affect the situation is also probably less noticed before. These people always talk about, the whole simulation, what's the error Mach number? People seldom to look to these details of the error Mach number at different density. And this is something.
Okay, so I might be trying to drive things to equipartition, but it's how I'm doing it that's mattering. Right? It's how I'm using the turbulence as part of my cascade of between the different components. We'll talk about fun.
Yeah,
Okay.
That's quite a good question. But I think no matter how you start with the initial condition, and they always approach the equipartition.
Yeah.
Because you start in very, very turbulent situation. Those energy will go compress the B field and become B field energy. So the equipartition, I call it Tai Chi in sublimation. It's should always happen. So shouldn't be one force is ultimately dominant.
Okay, great. Let's thank Hua-bai again. And move on to the next speaker, Tao-Chung Ching.
Hi everyone, my name is Tao-Chung Ching. I'm a JWST fellow of NRAO in Sapporo right now. And before I'm working for NRAO, I have been working for FAST for 5 years. So today I appreciate the organizers of this conference to allow me to have a chance to share my new result of magnetic field measurements in molecular cloud. Hua-bai already showed this diagram. So Zeeman is the only method to directly measure magnetic field strength. It is important, but it is extremely hard. For the case of survey of large telescope like Arecibo, GPT, around 30 meters. This is all the high confidence Zeeman detection we got so far. There's only around 130 detections, and all of them coming from the 3 tracers. H1 tracing the low density part, OH tracing the medium density part, CN trace the massive star forming region. Here is a quick gallery of the Zeeman effect. For source I emission like the Gaussian, the Zeeman feature is an S-shaped feature. We call it Zeeman splitting in source B. So this is for OH and this is CN Zeeman. There are 2 velocity components and 2 S features in the source B. Since there's only 3 tracers right now, so it's critical to find a new tracer. And my supervisor, DD in AOC, he proposed that HINSA, which is the absorption caused by the cold atomic hydrogen in molecular cloud, can be used a Zeeman tracer. The advantage of hints at that first, the Zeeman splitting factor is larger than most of molecules, and also it's in low frequency, so it's easier to reach high velocity resolution than high frequency tracers. And also one secret for Zeeman observation is that narrower absorption is better for Zeeman detection because this narrower feature will give you a stronger L-shape feature. And but things are still weak, so for many years effort of GPT or RCBO, people still cannot detect inside Zeeman. With FAST, we use about 8 hours, and this is the first PINSA Zeeman obtained towards 1544. So this green circle is a previous RCBO measurement of 11 microdaughts. These 4 sine circles are results from GPT, and we perform FAST observation towards the condensed peak of PINSA, and we obtained field strength about 4 microdaughts. The science impact of these results is that the magnetic field is about 3 to 4 times weaker than predicted in report diffusion, and also from the other works of this core, the chemical clock expect this core is less than 1 million year, still shorter than the typical report diffusion time scale. So these results doesn't favor recurrent diffusion. This is our first fast Zeeman result using the central beam, and very recently we finished the 19 beam Polarized commissioning. With this receiver, we probably can improve the efficiency of measurements by a factor of 10 than the previous RCBO GPT measurements. So this is the polarization parameters. So before the calibration, in terms of linear polarization, the error could be 1%, and the polarization angle difference is about 5 to 10%. Before polarization calibration, it's pretty good, I think. And after all of the polarization calibration, if you compare the side lobe in source B of FAST to RCBO, this is FAST. The peak of source B is about 0.4% of source I, and for RCBO is about 1.5%. So this is the key why we can obtain KINSA or Zeeman or FAST, but the other telescope cannot. Because in terms of this source B measurement, FAST is about 3 times more sensitive than RCBO. With FAST, this powerful instrument, we have built a small team working on a synergy between FAST Zeeman and the JCMT PO2. For FAST Zeeman, we can working on H1 PINSA and OH high redshift Zeeman observation. We have objects like low mass core, high mass alpha region, plug core, Fermi bubble, quasars, and we have created a small sample to cooperate with PO2 working on to construct the 3-dimensional magnetic field by combining Zeeman observation and the JCMT PO2 dose polarization. So this is one very first fast multi-beam Zeeman observation. We obtained this toward B227 from this CO contour in red and the PINSA contour in black. People expect it's a core just at birth, and we found that toward the center of core is positive magnetic field, which means the magnetic field is along the line side, point out. But in the envelope of this core, the magnetic field strength is negative, so it's pointing toward us in the other direction than the core center. This is not expect in the classical star formation because people could expect the variation of magnetic field strength, but not in the line of sight magnetic field direction. And the dream of this project is If we can use all the 90 beam of fast, we can probably do Zeeman mapping for molecular clouds. So we have obtained 29 hours last year. If we smooth the resolution to half degree, we probably will make the magnetic field strength around the cloud. And if these techniques works, we can apply it for the craft 2,000 hour project, and this will reveal the Zeeman map, the magnetic field of half of the sky. So this conference key is high angular resolution. So for fast, we observe magnetic field about 4 megapascals. But we need high resolution to distinguish if these 4 megapascals coming from a smooth uniform magnetic field within a fast beam, or is a patch-like magnetic field distribution, or is coming from a spot with very strong magnetic field. For VLA, we request 44 hours toward the same object. And here is a very preliminary result. This is the VLA source eye image. This is pinza absorption, the same as the black dashed line is the pinza color density obtained from ICBO. And these green contours are source V contours at 3 and 5 sigma. For these two spots, if the detection is true, the magnetic field is about 300 microgauss. And the good news is that towards this red bar, this is the H pinza showing the last page. We also obtained OH Zeeman towards the same spot with magnetic field about 200 microgauss. If this detection is coming from instrumental effect, this is the phase center, then the spot of inside OH should scale with the frequency, which means these two spots should separate by about 1 VOA beam. But they are the same at the same location, indicate there might be true detection. And this is a location where we obtain fast pinza. And surprisingly, this 300 microgauss detection is further away from the core center. The result is very positive because for the other source V spot, we actually cannot find pinza as shape feature. And also for the OH, we only obtained Zeeman in 1665. We cannot find Zeeman in the 1667 line, megahertz line. So we are still working on, for example, smooth VOA data to the resolution of fast, and applied the sino of fast beam to see if we can reproduce the fast 4 megahertz detection. So if the detection is true, what's the science behind this result? For fast, it's 4 microgauss and 3 Archimedes resolution, but for fast, for VLA, it's 100 times strength in 1 Archimedes resolution. So one thing is maybe our result is consistent with the first VLA CCS Zeeman towards TMC 1C, the other Lopez-coba, which measure the magnetic field strength of 1 milligauss, also at the edge of the core, at the center of the core. And also, if you consider the missing flux in source I, the lower source I will give you an overestimation in magnetic field strength. So, and also, I just learned yesterday is that, well, if there's certain variation in ionization cosmic ray, it is maybe possible. Well, my story is that here is the pinza. The pinza is larger, means the cosmic ray probably is higher. So it's harder to reduce magnetic field strength. So you can have 100 magnetic field strength remain at this location. But toward the other position, toward the core, The king size is weaker, the ionization rate is extremely low, and the reduction of magnetic field is more efficiency, so you got very low magnetic field strength in the other part of the core. Anyway, the lesson is that 50 hours for VOA is still too expensive. So in the end, I would like to appreciate the support of all my teachers. This is a point I made before I working in NRAO. So it's a revision of a point in legendary made by Guan Yu, the saint of the world in Chinese culture. The main point is that I am empty in my bamboo can to restore your kindness, and my bamboo knot help me to stand on my ground. So also I might not be the most beautiful, bright plant, but I will stand on in cold winter. Thank you very much.
All right, time for a question. Magnetic fields, bamboo.
So really, you're using the CCS at 230, 23 gas, right? For to get a Zeeman.
Right.
I was just wondering whether my 7 millimeter, 45 vectors, that they also works.
I really don't know. I think in the literature there hasn't been CCS Zeeman in 7 millimeter font. Well, I haven't calculated the possibility to use CCS, just no comments right now.
Okay, let's thank Tao-Chung again. And our next speaker is Jongsoo Kim.
Okay, so my name is Jongsoo from ASIAA. So I sent an email to Aran, probably some of you know her. So she actually spent Aran, she's Aran. Okay. She actually spent here ASIAA as a postdoc and working with Paul. And in fact, she sent me a quite long email and also made this one slide presentation file. So I want to share this slide. Here's Paul, and this is Jackie, and they came to Korea, and then they climbed Pala Mountain in Jeju Island. So they actually enjoy a lot. This is actually the middle point of Pala Mountain. And the first word that she come up with Paul is actually welcome on board. So I hear this word from the previous speaker. And the other one is actually mentor. Okay? So Paul is not supervisor, he's actually a mentor. And then she actually sent us a couple of messages. But also in her email, she got surgery in Taipei. At the time, actually Paul and Jackie waited in a hospital until the surgery was finished. The other one that she actually sent me is that when Paul visited Korea, he actually visited Aran's house. So there, actually Paul got comfortable and well treated. And also, he actually enjoyed the boiling system of Korea. So in fact, have the Korea actually boil under the floor, so which is actually quite good. So I'm trying to share this message. Okay. So let's go back to the science. So I'm going to give a talk on magnetic field distributions. So this work was done by my previous students. Now she is actually a postdoc at CUHK, and also the many people who actually joined this team. So the paper was published in 2. So mainly this is actually a methodology paper. So I will try to explain the details of the method. So I'm trying to encourage some of you to use this method. So trying to explain this paper. Okay, so today we actually got from several speakers on the general self-absorption method. So in fact, I don't like this method, but the people have used this method in order to measure magnetic field strength. But the way to measure magnetic field strength through this method is quite simple. So once you measure the velocity dispersion and polarization angle dispersion and the modesty, then you have the magnetic field strength on the sky plane. Okay, so which is quite simple. Okay? So this is actually motivation of this study. So we saw many polarization map. One of them is actually this example. So in fact, we actually are trying to get distribution of magnetic field strength on the sky plane. Okay, but people have used this map. They have a lot of polarization measurements. There are many points, but what happened is that they only got one value over all this region. Think about this is actually famous OMC1. So we have Orion BN and KR and Orion S. There are huge difference between this dense part and the diffuse vision. But they provide only one value for the magnetic field. Okay? Even the polarization observation is very expensive. You need quite long exposure time. So the main motivation of this study is actually trying to get distribution of magnetic field strength over the sky plane. Okay, so basically we are going to use two set of observational data. One is actually JCMT42, and the other one is actually JCMT top C8 So using this one, we try to measure the velocity dispersion, and using the port 2, we try to measure the angle dispersion. But also we actually use not only 850 micron data, but also the 450 micron data. So combining these two data, we can get column density and also the level density. Okay? So the idea is actually quite simple. Okay? So we have the polarization measurement over the four star formation region, for example. But we have to measure the angular dispersion. So what we propose is that you can actually set up the this small local section. Okay, so using this local section, where you can actually measure angular polarization, angular dispersion. Okay, and then you actually move this one 1 pixel, and then you can do the same measurements. So here are some details on how to measure the angular dispersion. So in fact, I would like to use the 5 by 5 pixel box, and then first measure the polarization angle from Stokes U and Q, and then you can actually calculate the mean direction over this box. Okay, this actually improves that within this box, the mean magnetic field direction is actually uniform. Okay, so later I will come back to this one, and then we actually calculate the angular dispersion using this relationship. So we actually repeat this one, then you got the distribution of magnetic field strength over the sky. Okay, so one thing that we look at whether the uniform direction distribution, uniform absorption of the direction over the box is actually correct or not. So we actually look at the concentric circles and put the box in here. So we actually move this box around the origin and outskirts, and then measure the angular dispersion. So in fact, we assume that the polarization segment is actually following this concentric circle. So here you have polarization segments, and then we actually measured the radius, like ratio of radius over the box, and then we measure the angular dispersion. So what we found is that once the radius, this ratio is around 1, still the angular dispersion is only about the 0.5 degree, so which is actually quite small. So at this, something like this position, still the uniform direction of absorption is actually quite good. So we actually trying to put these requirements in order to do the real analysis. The other one is that, so in order to remove like some polarization measurements from our analysis, so we actually measure the curvature of polarization segments. So this idea was actually introduced via Patrick. So once you have like 2 segment measurements, then you can actually draw a quite big circle, okay, which actually your segment is actually tangent to this circle. Then you can measure the other curvature arc. Okay. So what I did, so using this actually here, what I did is that we have the map of the polarization measurements. So if you pick up these 2 polarization segments, then you can actually measure your curvature and then put that curvature information in this position. Okay, you can do the same thing from this pair, do the same and do the same. So you know the curvature on these 4 spots. And then I take the average of these 4 values and then put that information at the center. So at every center, you know the curvature of your polarization segments. In fact, if the curvature is actually large, then they are almost parallel to each other. But if the curvature is actually small, then you have much variation on your measurements. Okay, so by doing this, we actually have measured, this is actually the curvature of the polarization segments. Okay, so we use each pixel as 4 arcsecond, and part size is actually 5 by 5, which means that the 40 arcsecond by 40 arcsecond. Okay, so in fact, so what we did is actually there are like a segment in here whose curvature is actually smaller than the part size. So we are actually trying to remove this one from our analysis. Also here, this one, the curvature of this one is actually too small, smaller than the part size. But anyway, so we actually measure the curvature of curvature at each pixel of the segment. Then, as I introduced already, how to measure the angular dispersion. So here is actually the angular dispersion over all regions. So at each pixel. Okay. So there are places where we cannot actually measure the angular dispersion because of the too much variation over here. And then the other part is actually quite similar to the other two, quite straightforward. Okay, so in order to get the, in order to use Chandrasekhar-Fermi method, we have to know the eventually number density. So what we did is actually we used ratio of 850 and 4050 micron, and then get the dust temperature. And then we use this relationship. You can hardly see, but the anyway, we actually got the H2 column density. And then eventually we have to have some number density. So what we did is actually we look at the literature and find out the other measurements of the number density, especially at the dense parts. So what we did is actually we tried to match the number density measured on the previous literature, and then give the other depth information, which is around the 0.2 parsec. Okay, so in a sense, this is actually quite simple, but the number density is actually proportional to current density. So in a sense, it is actually acceptable. Okay, and then we also measured the other velocity dispersion using the CA line profile at each pixel. But there are cases where you have 2 peaks, and so we actually trying to pick up the one of them. So we actually did some comparison between the C8 flow map and the dust continuum C8 channel map. So probably this is better. But there are pixels which we cannot measure the velocity dispersion. Okay, so eventually we got the magnetic field distribution over the region that we analyzed. So in fact, we got magnetic field distribution not only for 4050 micron, but also the 850. So this is what we get. So in fact, the Petter wrote a very nice paper she actually measured the magnetic field strength over all regions. But our mean value of the magnetic field strength is around the 6.6 microbars for 50 micron case. This is actually 6.2, so which is actually quite consistent with our result. So one thing that you can do is you can now learn science, okay? And for example, you can measure the EN relation, and then you can measure the copper. So for example, actually I mentioned about this vector. So in fact, there are denser parts. The kappa factor is actually around less than the 0.5. So this actually consistent with the prediction of ambiguous diffusion model. So another one is actually mass to flux ratio. So we can actually easily now measure the mass to flux ratio of the whole regions. So in fact, the people actually use the mass flux ratio in unit of the critical density. So what you can see in here is that the mass to flux ratio in critical unit is not depends upon number density, but depends upon column density. So this is actually the three-dimensional magnetic field strength, right? Not the magnetic field strength over sky plane. But anyway, so we actually used the other sky plane value. That's due to the fact that the line of sight in this line of sight magnetic field strength in this region is quite small compared with sky plane value. But this is what we get. So most of the blue part is actually a subcritical, so magnetic field is strong, but the other red part is supercritical. So this is actually quite consistent with the density distribution. So in fact, we have the denser clump there. So another one, you can actually measure the Alpine Mach number here. So the most of the region is actually transalpinic or subalpinic. Okay, so we also did the same analysis for the Monarch 2. This is actually the polarization measurements, and this is actually the distribution of the magnetic field strength over the sky plane. So this is actually conclusion. So I encourage people to use this method, which is actually quite straightforward, and you can get more information from your polarization measurements. Okay, thank you.
Okay, so in the interest. Okay. All right. So anyway, in the interest of time, I think we'll leave questions for Jongsoo for lunch, and we'll have one more talk before lunch, which is Jose Miguel. No? Okay. Wait a minute. We actually will have time for a question.
Go. So all the announcements, lunch is ready outside, so we'll come back at 1:30 or 1:45. Yes. And second announcement, since we have some space for posters, and now is the chance for local participants, postdoc students, if you have posters ready,